My name is Spencer Wilson, and for kind of, this is concluding what we were just talking about the previous ones, I'm not really sure, but for my report, I covered torsional stress and shear centers. And the first thing to note is that's the smartest animal on the planet. And I'm not that smart, but I did find one issue with O'Hara's Cocker Spaniel. It doesn't have opposable thumbs. So I went to the second smartest animal because he can use a wrench. And that means that I can also teach the gorilla what torque is. So in covering any kind of twisting in a member, it's best to kind of understand the nature of it. So basically, what we're normally taught is the actual in-plane bending of a member. And this is more looking at actually the axial twisting of a member. So just imagining, like a wrench over twisting something, and that's how you're generating torque in a shaft. So one of the earliest ways to kind of look at it was generated by this guy who has an incredibly long name, but point being, St. Venant created a general principle that led to some very simple ways to analyze twisting in a shaft, which is something that we covered fairly early in strengths and materials. And the most important thing to take from this, from his analogy, is basically looking at a cross-sectional area which, when it is subjected to twisting, it does not actually change its cross-sectional area. So in that instance, in using the other things that you talked about through that, you can kind of determine that, say, a circular shaft, if it's twisting, it stays a circle the entire way, but the only thing that's really changing on it is that one relative to another has undergone some sort of twisting strain that has actually rotated it relative to the other end. And that because of the nature of how the torsional stress spreads out from the center, that it's actually always tangential to the point at which it's cut, which you can see here relative to this twisting moment. So therefore, the formula for it is relatively simple, derived from the normal stress equations to get to it. And the cylindrical cross-section, or the cylindrical tubing, anything like that, it's the easiest to analyze and by far is the best when subject to any kind of twisting, but there aren't very many good examples for using it in a real-world application. So this is one that's on a very grandiose scale. The entire network of structure that makes up the exterior portion of this building is this intricate lattice of circular tubing that goes throughout it, which works really well. It's very amorphous shape, and then all the tubing and everything is actually twisting, in a very easy to analyze way relative to the rest of it. But it was very cumbersome to build, the connections aren't very pretty, and it had a massive budget because this is for actually a World Expo. Now this guy actually gave an analogy that's best for talking about any kind of thin plate members, like what we're used to with W shapes. So his was to analogize any kind of cross-sectional stress from twisting to a soap foam. Now, Ludwig Prandtl basically started out by saying, imagine that if you were looking at a W shape, you looked at a membrane or something flat, and then it had the cross-section you were looking at cut out of it, and then a thin film of some sort of material stretched over it, and then you applied pressure to it so it deformed. So basically what that would do is you would actually get this very nicely conceived relationship between the way that that form deforms relative to the actual bend or twisting stress that's happening inside of it. So basically, similar to the circular member, the central point of that film where the slope is 0, the torsional stress is actually 0. And then when you go to the edges, that where the slope is the greatest, that means that the stress is actually the greatest there as well. So you kind of get this contouring map of any shapes that aren't, perfectly symmetrical. So, and then from there he theorized that you can generate Prandtl function, which is basically the stress relationship that you can then use to derive or approximate the actual torsional stress happening inside of a member. So this is actually kind of going back to St. Venant's theorem, and that you're looking at this cross-section, and you kind of look at the differential element of it. And so the y component, the x component, they both form together geometrically to create that tangential torsional stress that's happening inside of it. So it creates these boundary conditions that must be satisfied with any kind of derivation for the torsional stress inside of the member. So, and this is kind of like, the nice conclusion to it, which it actually relates the slope to the actual force applied, which was something very relevant in this analogy, in that not only does the slope have to do with the torsional stress, but also the area underneath that curve formed represents the magnitude of the force applied. So this is just kind of a loose example to show the idea behind deriving equations, because again, Prandtl's method is more of an approximation than anything. So looking at this, you're deriving the Prandtl equation based on the visual deflection on that kind of cross-member shape, and then using that in relationship to the applied force to generate the final equations for the twisting angle, and likewise the maximum or whatever stress is incurred inside the member. Now, the final thing relative to that is actually dealing with the orientation of it. So what Eric was talking about relative to kind of asymmetrical bending and things like that, everything has, or all cross-sectional members have what's called a shear center, which is effectively a point about which, if any force is applied relevant to it, then the only forces incurred would really be shear and bending itself. So that kind of lends itself to how you actually place members, why we load things perfectly down the center as opposed to on the edge, because then you get messy things like this, where say a W shape would start to twist. So in conclusion, any kind of torsional events or stress incurred in a member have a great deal to do with the actual geometry and orientation. Stiffness analysis can be applied to it to analyze it, but if you're going for a more kind of quick and dirty method for analyzing, you can go through the Prandtl method and then the stiffness method, which is more similar to what we've been deriving in class. That would also generate an accurate result. So, any questions?